Hello, I'm David Porter. Angel Mancebo is in the room, and today we'll be giving a tutorial on parallel computing using resources on MSI's Agate cluster. We'll start by talking about the job queues that are available, which is a great overview of the resources that are available. But we'll dig in a bit deeper into the hardware that backs it up. Um, Angel will talk a bit about the GPUs and their nature and programming on them, and then I'll continue with a variety of constructs for parallel computing, including task arrays, shared memory or thread parallel computing, and distributed memory or MPI computing. We have examples that posted at this website here, and this will be repeated several times, where you can pull down working examples of the codes we'll be illustrating. So to start off with the queues that are available on Agate, basically there's quite a few of them, and they reflect a rich heterogeneous cluster with lots of different resources. There are quite a few standard compute nodes, but and there are a variety of queues that will allow you to focus in on the resources that you need for your particular application. So, for example, there's MSI small, and there you get one node, and you can ask for as many as 128 cores. You can ask for as many as 96 hours of wall clock time for running on that node. And there's a variety of memory that's available on the different nodes that are in that queue. A range that you could, upper range you can ask for. If you want to extend beyond that and run across multiple nodes, which are particularly good for message passing and MPI programming, there is a large queue which can allow you to ask for more than one node and up to 32 nodes. With 128 cores on each, that gives you 4,000 cores to work with. And you can actually go beyond this, but you need to work with MSI staff in order to ensure that your code is going to run efficiently. And we need to coordinate as to when the job starts, since it would be using such a large fraction of the resource. And then we have big memory queues. We have queues that will partitions that will allow you to use GPUs that Angel will talk about. And then we have some preemptible queues which allow you to, which are likely to allow your jobs to start sooner, but they can then be preempted. So you only want to use these queues if you've built in a way for your job to restart, even if it's taken out or deleted in the middle of running. That can be handy for ensuring that the queues are filled and using every last bit of the resource. And so there are a whole variety of queues there listed in detail at this website here. And supporting all of this is a network of nodes. It's in a fat tree topology of InfiniBand fabric. And so there are basically these core switches, 5 of them, that are at the top of this fat tree, or the root, depending on how you want to look at it. And they connect to 9 of these leaf switches that in turn connect to quite a few nodes. They can be, each leaf switch can talk to as many as 50 compute nodes. They're not all completely populated, but this gives us hundreds of nodes, each of which have 128 cores typically on them. These standard compute nodes that are particularly handy for scaling up with a heterogeneous form or homogeneous form of computing, I should say, look like this. They are these AMD nodes that have 128 cores in all, that are on 2 different processors, so 64 cores each. In turn, they have these banks of 8 cores within each processor that share a third level cache. And then each one of these banks have a local third level cache on each one of them. And they have second level cache as well. The idea here is that there's quite a lot of resources, even on a single node. 128 cores, typically 512 gigabytes of memory, and an aggregate of 16 of these 32 megabyte caches, for a total of 512 megabytes of third level cache that's local to the sets of 8 cores. This gives it a lot of flexibility in how it can run. And with this much cache memory, you can typically run very large applications and data intensive applications very efficiently on this machine. And I'll illustrate how you can take advantage of this cache hierarchy in some of the examples that we'll be presenting later on. The HP resources on Agate are, as I mentioned, it's a heterogeneous cluster. And so you have the standard compute nodes, there are some large memory nodes, and then a whole variety of GPU nodes that are available. This set is always changing, but Angel will talk about some of the details of some of the more common GPU nodes and how you can take advantage of them. So, Angel, did you want to start here?
Yes, thanks. So we have two different kinds of A100 nodes. One is A100-4, and the way these work is that they are arranged in the topology on the right. They have 64 CPU cores, and then we have 4 A100s that are arranged, connected directly to each other. And that's with 600 gigabytes of bandwidth per GPU. Then next slide.
Mhm.
The A100-8 nodes have 8 A100s in them, but they're configured a bit differently. You have the 2 CPUs that go to 4 GPUs each. And then to go between GPUs, there's this NV switch that connects them instead of going directly to each other, like in the A100-4 case. Next slide. So if you want to request a GPU for your job, you would probably, for a batch job, you would want to use the MSI GPU partition, though it's not necessary to use this one. You can use the interactive GPU partition as well. But you would specify the MSI GPU partition, and then you specify your resource. So you add this extra line with GRES that stands for generic resource, and you specify you want a GPU, then you specify what model GPU you want, and then you specify what number GPU you want. Next slide. If you want an A100, but you're sure you want to use multiple A100s and you want it to land on the A100-4 partition, you could also specify directly the A100-4 partition instead of MSI GPU. And then, of course, you would specify that you want an A100, that you want multiple A100s. In this case, 2. Next slide. So when you use GPU jobs on Agate, if you ever need to invoke the CUDA libraries from our modules, you should be using at least CUDA 11. Right now, on the GPUs, we're up to CUDA 13. So use at least CUDA 11 whenever you're using those libraries. When you want information about the GPU, like what the GPU is doing currently, how much memory is being used up, etc., you could use the NVIDIA SMI command, which gives you some information about the GPU. Then there are lots of ways to parallelize GPU jobs. So you can use something called OpenAC, which is similar to OpenMP, but it's portable from CPUs to GPUs. So it lets you do things in parallel, but then take your code that can run on a laptop and then run it on a GPU. Then CUDA is an extension of C++, and it's for writing NVIDIA GPU kernels. I'll give an example of what that looks like. Nickel, NCCL, pronounced nickel, is for multiple NVIDIA GPUs, and it's similar to MPI, if you're familiar with that message passing interface. It's for doing collective operations. between GPUs. And then you can combine the different methods with OpenMP and MPI as well. So if you have jobs across multiple nodes, or if you want to parallelize things on the CPU, you can combine them with the parallelization on the GPUs. Next slide. So OpenApp, what's good about it is that it's simple. So it's like OpenMP, and you basically have directives that you put into your file, and it's a fairly straightforward way of parallelizing your code. You generally don't need to explicitly copy your data. You don't need to explicitly copy your data to the GPU device. It'll do that automatically when you port it to the GPU. It's portable, so it'll run across multiple kinds of GPUs, in addition to CPUs. So it's not just we only have NVIDIA GPUs at MSI, but you could also use it on AMD or Intel GPUs as well. So it could run on a different supercomputer if they had a different kind of GPU. Next slide. So this is an example of OpenAC. So it's similar to OpenMP, where you have these pragma statements that you put in, these pragma directives, where here you have pragma ACC kernels for the entire block, then pragma ACC loop independent for when you want to parallelize the outer loop in this case. And this is basically a somewhat of an embarrassingly parallel problem where you're updating data in a new array, and you're reading from another array. Even though you might read the same data from multiple processes or threads, you're not writing at the same time. So there's no need to do things like atomic operations to prevent any kind of data races. Next slide. So CUDA. So CUDA is a library for interfacing with NVIDIA GPUs. It also refers to the language, which is basically C++, for making NVIDIA GPU kernels. The compiler for CUDA code is NVCC. And a lot of the software that runs on NVIDIA GPUs, like PyTorch and TensorFlow, which are two of the biggest ones, can use CUDA in the backend. So generally, it's actually very unlikely that you would ever need to write CUDA by hand, but it's good to be familiar with the library itself and what it is if you ever use these other tools like PyTorch and TensorFlow. Next slide. Just so you're familiar, this is an example of some CUDA code. So here there's a kernel defined as CUDA hello, which prints hello world from GPU. Then in the main function, it's invoked. You'll see that it says CUDA hello, then there are these strange angle brackets. These angle brackets are how you invoke CUDA kernels. And in between the angle brackets, you have 1, 1. So the first number is the number of thread blocks. The second number is the number of threads per block. So the memory is arranged in these blocks of threads and then in threads themselves. So it's almost like a 2D grid layout. And then at the end, it synchronizes and returns 0, just like a normal C++ or C program. Next slide. So Nickel can be used for distributed training across multiple NVIDIA GPUs. And it implements operations that are similar to MPI, which is the message passing interface, for doing communication between GPUs. It can also be used in conjunction with MPI as well. MPI is normally for CPUs. Similarly, like with CUDA itself, PyTorch and TensorFlow have Nickel support. So when you're doing things like distributed training, you probably don't have to actually be aware of exactly what Nickel is doing. It'll happen in the backend, but it's good to know what it is so you know what's going on. Next slide. And then you can take it from here again, David.
Okay, great. Thanks.
Thanks.
Okay, so there's quite a lot of information that we'll be presenting here, and really this is because there's so much to cover. Think of this as really an overview. And so these are pointers to a lot of different frameworks that you can use, and we can provide documentation for digging into any of these that are of interest and of use to you. So I'll continue now with the first kind of parallel programming that I'll be reviewing here with the task arrays. And basically, I'll start off with the basics of how you submit a job with a task for a task array on Agate using the Slurm batch queue. And then I'll give a specific example of how you can use this to support a data-driven workflow. So the basics are actually quite simple. You have to start with, of course, an application that you would call from a normal, usually a bash shell on one of our compute nodes. And the bash shell is really well supported for background jobs that this is really intended to focus on. Since this is going to be running in the background, and since it's going to be using a larger amount of resource and specific resources that your application needs, you need to request those. And you can do these with these statements here. These are resource request statements for the Slurm batch queue. So it always starts with a sharp and S batch, and then the specific resource that you're requesting and how much. Interestingly enough, in a bash or any normal kind of shell that you would be running under Linux, a sharp will typically be interpreted as a comment statement if it's just a normal shell. And so, in fact, you can run these, you can usually run a Slurm script as if it just interactively from the terminal. And the only limitation there, of course, is that it's not really running in a job and you haven't really gotten the resources that you may need for your application. But it's a great way for debugging the basics of the script, especially if you don't use much resources in your testing and development. So in asking for resources here, you ask the -n, there's a variety of ways you can specify this. The example I have here, -n, will ask for a number of nodes. And so here, I'm going to ask for one node per task. That's the way that this is interpreted. So a task array can actually have many tasks associated with it, but each task will only require one node and it will be run on one node, but probably not using the entirety of that node. And in fact, for this lightweight application, I'm really only asking for one core on this node and a very short amount of time. And I'm specifying also an output file with this -o flag that will actually use the job number. That's where this %A, capital A goes, and then the task array number where this % lowercase a goes. Now, the secret sauce that allows you to use these task arrays to do a large amount of work is this shell variable that gets set up for you by the job manager when it starts up your job. This Slurm array task ID. So this is a shell variable, and as the case with most Unix type shells, including Bash, if you put $1 in front or $1 with brackets around it, this will return the value at that point. And so here, this job is just an example, and all it's going to do is it's going to report which Slurm array task ID this particular task got, and also report the name of the node that it was running on, just as an illustration. But what you would do in a normal job is to use this task ID to derive which piece of the work you want to do, and that will depend on your own workflow. For example, you might have 100 files you want to process, and each file may be neatly numbered 0 through 99. And then you could then use this task ID number to construct the name of that file, and each task would do it process a different file. That's one of a myriad ways you could use this. It's up to your imagination and your programming style, and really depends on the kind of application that you're using here. But this just illustrates how you run it. So, and what it will look like, more or less. So, to submit this, you have this in a file. Um, do one task is what I've named it here. And you would submit it with this sbatch command. And you do this dash dash array equals. And if I want to run 10 tasks numbered with IDs 0 through 9, I can use this syntax here with this array equals 0-9. So that would give me 10 tasks in all. And then I give it the name of the script. This will submit a job. And then because I'm putting standard out to these names that look like this, once the job is finished, I will get 10 files that are very neatly named by this the overall job ID number and then the task ID number because I specified that this way up here. And in each one, we'll have one line that's associated with it. And I just neatly listed them all by using a Linux command grep to look for task, and that's why that's in red here. And neatly enough, the task ID numbers run 0 through 9, one for each one of these output files, and each one of these output files correspond to one of the tasks that got ran. And so that in a nutshell is how you can set up and run task array. But just to illustrate this a little bit better, I wanted to show a working example with a data-driven workflow, very similar to the kind of work that I'm doing, analyzing satellite imagery. The idea here is that we'll have a lot of data staged on MSI's Tier 2 storage, and we're going to sweep through this large volume of data, processing each item in the same way and producing some derived results, some highly reduced results that we can then combine together after the task array has run and see an actual result. I'm using Sentinel-2 data, the European Space Agency's Sentinel-2 missions, 2 satellites in a constellation, A and B. They are taking satellite images of the Earth's surface at 10 meter, 20 meter, and 60 meter resolutions. At least they will cartographically rectify the imagery in a variety of different bands from ultra blue all the way to shortwave infrared. And the repository will, after they've mapped these images onto the globe, they'll break them up into tiles so that they can readily be accessed for just the part of the globe that you're interested in. And I chose a tile that's basically covers Minneapolis and a 100 by 100 kilometer area patch that contains the Minneapolis area. And I'm going to follow that for 6 months of data that it took, May through October. And what I will do for the highly reduced product, as an example, is I will look at the green band of radiation, band 3, and just look at the statistics as it varies through time. The data as the repository presents it is broken up into these tiles, like I mentioned, and it's available on the days when the satellite actually physically flew overhead of the particular region that you're interested in. And so there's each of the satellites has a 5-day repeat, and between the 2 of them, you might get 2 or 3 observations at every 5-day period. So it's a bit of an irregular sampling. Across this 6-month period, I had 86 such files. Um, and I want to process each one of them in turn. Here's a list of four of them, of four of the 86. So this is just the file names that include the satellite S2, A or B. Um, MSI here stands for multispectral instrument. We'll be looking at level 1 or top of atmosphere, and level C is for the cartographically rectified imagery, which makes it easy to map it onto the globe. And then it has the date of the data take and actually the time when the data take started. I'll be focusing on the state for labeling here, but reading into the zip file to get the imagery and so forth. Now, with 86 files to process, the way I decided to parallelize it in this very simple example is to, in one of the simplest ways I could think of, which was to take the full set of 86 files and split it into 20 pieces with either 4 or 5 lines in each of these files, each line corresponding to one of these zip files that corresponds to one tile on one day. And so by using this Unix split command, I can take that full set of files that I had listed in this file here, full set of zip files, and split them into 20 different files, each one with a unique set. So all I need to do now is run a task array that basically each member of the task will only look at one of these files and process the files that are in that one. So I have a script which implements that. And again, I'm asking for one node, one task, and one CPU on each one of these nodes. It will only take a few minutes to run, so I ask for a short amount of time. And I'm mapping standard out just to record the output, but I won't be actually using this file. I'll actually be saving the reduced results into a smaller file that I'll reference later. I find it handy in doing this data parallel, data-driven workflows to have each one of the tasks make its own directory to work in, simply because it makes it guarantees that one task will not collide with another one in terms of the namespace of the files that they're generating. And it also makes cleanup very easy. As each task finishes, it can simply blow away the entire directory, and you don't have to worry about it interfering with any of the other tasks. So I derive a work directory based on the task ID number and create that directory and go into it. And then I'll work in that. This one task will work there from here on. I have a Conda environment that I've built that will support the raster IO set of modules under Python that we'll use for reading in the image data. And then I get the zip file based again on the task ID number. So this will correspond to one of those files that was split, which will have either a list of 4 or 5 zip files to process. So then I have a for loop that loops over each one of those zip files. It will pull it from tier 2 storage, unzip it, and then run this Python script that will analyze the data in that zip file. And then once it's done, it will clean up or remove everything and continue on to the next. And that's really all there is that you need for this kind of a data-driven workflow. Just for completeness, I have the Python script that actually does the work. And basically all I do is, since I've already unzipped the file in the script, and I know the directory structure that this data is stored in, I know the directory to look, and the name can create a file filter that will point right to the file I'm interested in, which is going to be band 3. It's stored in JP2 format. It's an advanced image kind of format. I'll extract from the file name the information for the date that I'll construct just from the parsing out the the characters from the file name that correspond to the date of the data take. And then I use this raster IO module to read in the data for band 3 as a Python array, a NumPy Python array, which I can then use NumPy methods like extract to only extract the real data. I know that the value 0 corresponds to no data in these files. And then I can use NumPy percentiles to get these percentiles 1, the quartiles, and 99th percentile, and then just print them out along with the date for labeling. And that's really all there is to it for this simple kind of processing that illustrates how to do this data-driven workflow. When you go to submit this, you again would use this sbatch command and you'd give the dash dash array. And here, since I want 20 tasks numbered 0 through 19, it's just 0-19. And then I give the name of that Slurm script that runs this. And then I can list the jobs that I have running. And here I'm using this SQ command, which is what you use to list jobs that are running under the batch queue. And there's lots of arguments you can do this. I use -L for a long listing, which gives me all these details on the jobs. And then I do a -U, and I have $user here so that I'll only list my own jobs. Otherwise, it would list all the jobs that are in the queue, and that gets very, very lengthy. And by the time I submitted this, ran this SQ command, all of the jobs are running. So I had 20 jobs running at the same time, processing data in parallel. When they finished, I ended up with these 20 files where the output went. And I can just use a simple Linux command to concatenate all of these together. I sort it to make sure that the dates come out in order and end up with a file that looks something like this, where I have these percentile values. And then you can use my favorite plotting package. I'm using matplotlib here to plot the first, the 99th, and the median values in green basically the digital number that came out. I could have scaled this to something like reflectance using some of the metadata, but I kept this example simple. And the large amount of variation actually mostly corresponds to the change in cloud cover that you're getting from day to day. But that's an example of how you can do a data-driven workflow using task arrays. So we have some documentation posted here on Slurm job arrays that will describe this in more detail with the options that you have available generally using Slurm job arrays. And then for the MSI queues, there's a few more pointers here, which might help direct you to details of how you want to submit these jobs, depending on the resources that you need. The next example is on thread parallel or shared memory parallel computing. And Agate is a really great cluster for this kind of a thing because of its large, high core count, large memory nodes. With 128 cores and typically 512 gigabytes of memory and a substantial amount of L3 cache, this turns out to be a very powerful and flexible platform for doing these kinds of shared memory kinds of applications where you may want to run many threads to get a lot of compute power and get a faster turnaround time for your result. But you have application, which needs quite a lot of memory, if you can fit what you're processing into 512 gigabytes um, of memory, then you're good to go on just using one node. And some kind of a thread parallel application might work very, very well in your workflow. So I'll be covering how you submit jobs for that will support this kind of thread parallel application, and I'll give an example using OpenMP that demonstrates how you can get very good scaling on compute intensive kinds of applications. So the um, Slurm script, again, is going to look very similar to what we've seen before. You're going to have resource requests with these sharp SBatch lines that begin with sharp SBatch. Again, because this is going to be shared memory, it'll just be running on one node. And because it's running on just one node, you can have it run in the MSI small queue. But now you'll probably want to ask for more cores or more tasks per node. And you can ask for as many as 128 on a standard compute node. And you may want to ask for more time. Here I'm asking for over 4 hours of time. Since these threaded codes tend to be compiled rather than scripted, you'll be running an executable, and you'll want to load the environment that you built the application in, or more generally that the application was built in. For the OpenMP threading model, you can control the number of threads in a variety of ways. The ultimate fallback is usually set up in the configuration of your shell, and it will typically correspond to the number of cores that you have available in that shell. So if you ask for 128, the fallback would be 128 threads. You can supersede this by asking explicitly for threads with this OMP num threads. And here I'm asking for 128. I could actually ask for more or less than the actual physical cores, depending on what I'm doing with them. You can oversubscribe the number of threads, and that can actually be effective if you're anticipating that the application might have threads that are stalling on maybe waiting for memory or even a disk or network access. And so some can keep busy while the other ones are stalled. That can be a good reason for asking for more threads than are actually you have physical cores. But typically for number crunching, a general rule of thumb, at least to start off with, is to ask for the same number of threads as the cores you'll be using. You can also set threads inside the application in a variety of ways, either in if it's C, a pragma statement, or in Fortran, a compiler directive statement, when you start the parallel region, and I'll be illustrating this, or you can actually programmatically set the number of threads in the code itself. So there are a variety of ways you can set the number of threads that you're using. Once you have your environment set up in terms of the runtime libraries and perhaps the number of threads you want to run on, you can then just run your application like any normal application with just a path to it. And if it's a compiled C or Fortran code, it will start up and run your program. The example that I chose to illustrate how you can get very good performance is a classic compute-intensive problem, an n-body problem where I'm explicitly calculating the forces across a set of n bodies. And so for the state of the problem, each particle or body in this problem will have a mass, a 3-vector position, and a 3-vector velocity. And that will run from, the index here will run from 1 to n, corresponding to n different particles. They might be stars, they might be galaxies, they could be molecules. Um, if it is like such an n-body problem, then what you'll typically have is that the time rate of change of the position is just this velocity. But then the velocity changes in accordance with the force on it, divided by the mass to give you an acceleration. So that'll be the rate of change of your velocity. And the force, and this is where it gets computationally intensive, on each particle depends on the locations of all the other particles. And so you have all these pairwise forces that that you need to calculate in order to get the total force on that particle. And since you're calculating in principle n forces on n particles, you're doing n squared um, units of work. If you double the number of particles, you'll be doing 4 times the work just to do this force calculation. And I chose this because it has been so common for number crunching programs through the years, and there's quite a lot of examples that actually will use something very similar to this. Galactic clustering, stellar dynamics, electron plasmas would all look something like this. Even molecular dynamics, although the pairwise force might be different um, between molecules. Um, and even something like genomics would fall into the same kind of pattern that I will illustrate for running this in thread parallel, because a common compute-intensive task with genomics is you're looking at pairwise comparisons of snippets of genes. So that's a bit more of a stretch in terms of how you would need to modify the code, but it's still layers of commonality are still that one, it's compute intensive because you need to sweep through all of those pairs. And two, I'm going to illustrate a way that you can get very good performance on very large memory problems by reusing cache. And these genomics problems can benefit from that because whether you're doing a force calculation or you're doing some kind of a comparison between sequences of DNA, you have to pull that memory into the processor and and then do the compute work. And so regardless of what work you're doing, what turns out to be the bottleneck oftentimes in getting really good performance out of this hardware is how the memory flows into them and how you can reuse cache. And I will illustrate that a bit just to show what can be done and what factors may be important in real applications, that whether or not you wrote the code yourself, what things might limit or enable good performance. So the example I'll give is in Fortran. It could be in C, but I chose the Fortran because it's syntactically very simple. And really and you can implement this in almost any language, but the concepts will be pretty much the same for the kind of algorithm that I want to follow. However, the parallel constructs, it's very nice for illustrating the syntax and the how parallel thread parallel computing actually works. The whole idea behind it is that we will start a normal program, might be in Fortran, it might be in C, and it's just going to be one process. And that process has its own memory address space, like any of the other processes that are running on your system. But with the OpenMP libraries, it has the ability to fire off multiple threads that can all see the same memory address space. The way you do that is you start a parallel region. And this particular program is very simple. It's just going to have one parallel region that will be started with this compiler directive here and end down here. And all of this will between all these lines in between and the subroutines that are called within them will all have the specified number of threads running at that time. You can discover which thread, uh, uh, and here's a subtlety to understand what's going on under the hood with thread computing, is that each thread is its own executing its own set of instructions. It can have some of its own local memory, even though there's some shared memory involved. And here I've declared such things as the thread number and I1 and I2, which will be the range of particles that this thread will update, to be local to the thread. And so that's private to the thread. And so I can discover my own thread number. And you can think of this very similarly to the Slurm task ID number, this is your hook or your way of deriving which piece of the overall problem this thread is going to do. It's just like the task ID number in that sense. And so here, the way I've decided to dice up the work is that each thread will update its own range of particles or galaxies or bodies. And then it will do that by, in this iterative loop that will run through a set of time steps. It'll calculate the acceleration on the particles based on the particle positions. I'll do a barrier sync to ensure that they use the calculations for the accelerations all use the same, the positions from the same time, the correct time before they're moved. And then after they've all finished calculating the accelerations and hit this barrier sync, I'll then I'll update the velocities and the positions based on the acceleration. And then I do another barrier sync to make sure that they're all updated before I go back and do the next time step. So I need to have these two barrier syncs in order to for this to work properly. Otherwise, some threads may rush ahead and be using positions that haven't been updated yet, for example. And really, that's in a nutshell the way you can use a thread parallel code. There are work sharing constructs, as they call them, for individual loops. And if the loops do enough work, they can be quite effective, and you can incrementally change a code that was serial to parallel. However, those will typically not be anywhere near as efficient as something like this, because there's substantial overhead every time you start off a parallel region or even manage a parallel loop. And that overhead will degrade your performance. And what's more, if you're incrementally changing one loop after another, then unless you do every single loop in your whole code, you will have some serial parts of your code, and they will ultimately limit how well your code can scale. So when I do thread parallel computing, I like to do it in this very coarse-grained way that allows each thread to just basically run independently, other than barrier syncs where they're absolutely needed. This Fortran code uses this common block to keep track of the variables that will, for example, the state variables for the position, the velocity, and the acceleration, as well as the control variables like the size of the time step, the number of particles, and the gravitational constant, for example. And then I have some of these auxiliary variables which will control the parallelism in terms of, for example, which range of particles each thread will do. And also I have a chunk size that I could allow as a control variable, which can illustrate how I can get better cache reuse by doing calculating the force calculation in chunks rather than sweeping through all the variables, all the particles, every sync in the simplest possible way. Um, then to initialize the problem, uh, because remember in that main code, this initialization step was done first before the calculation really starts. And so I set up some of the runtime parameters, but I read in also these controls for the number of steps it'll run for the um, the number of threads that'll run. So I'm using this a method where I can programmatically set the number of threads right in the code itself, and then the chunk size that I'll use for cache reuse. Um, then I set the ranges. So this is just going to set consecutive ranges for each of the threads. And then I can specify the number of threads with this set num threads call. Passing it the number of threads I want to have in each parallel region. This doesn't fire off the threads, but it sets the what will now be the default number of threads to run on when parallel regions start. And then I have an example of first touch, which basically is a trick you can do to help ensure that data is coming, each processor is pulling data from a local bank of memory. Remember that NUMA architecture that I talked about earlier, that is very common for virtually all high performance computing platforms with many cores, that some chunks of memory are going to be closer to the processor than others. Whether they're levels of cache or even memory banks that will typically be closer to some sets of processor than others. And in order to get the best possible performance, you want to minimize the basically the bottlenecks of pulling memory in from main memory or even from cache and having it run with as many independent lines into the processors as possible that don't collide with each other. And the way to do that is with this first touch command, which is a common trick. Then I initialize the variables, and what I'll talk about here next is this first touch. So basically, what I'm doing here in order to ensure that the memory is going to be committed to banks of memory that are close to the cores is I'm going to take advantage of the common technique that that the task scheduler on the process on the node uses for the resource manager. That when a process asks for something like memory, it will automatically try to do the memory that's closest to the core that's actually asking for it. So what I'll do is I'll fire off a parallel region, and then I will use this range that each thread is of the particles it's going to update, and then I just assign them to 0. And what this does is at this time, this is when the memory is actually committed to in physical memory. Up to this point, just because I've declared the array doesn't mean it's committed any actual physical memory. For efficiency's sake, the systems will typically not physically allocate banks of memory to part of an array until it's actually used or touched. And so this first touch convention, which is still pretty universally supported, allows you to, within the program, have the thread touch memory that it will be going back to over and over again. And in that way, it will minimize the memory traffic and maximize your bandwidth between memory and the processors. So this is a trick that can be very effective depending on the application. Okay, and then we move on to the force calculation. And then here's where I'm using this chunk size. But basically, think of it this way. I'm calculating this force, and I need to do this for each particle that I'm going to be calculating the acceleration on. And so So I'm going to have to run over the particles that this current thread is updating. Because remember, when I started the thread, the parallel region, I got these values for I1 and I2 that correspond to a consecutive range of particles to update. And so I'm going to be updating those, but I'm going to be doing it in these chunk fashions so that basically I'm in this force calculation on one side of this difference in positions to get the displacement between the two particles. One is always going to be the particle I'm updating, but the other one is going to be any of the other particles that are in the system. And so what I want to do is reuse those particles that were assigned really to another thread, so that when I cache them in to calculate this first, I will reuse them again and again across all the particles I'm doing the calculation on. That's conceptually what's going on here. So it's a trick which made this loop a little more complicated, but can actually produce better performance by reusing those the data that you've already pulled into cache. And so it will then do the force calculation and sum them in to this local array that then gets summed into the full array. And that's how the acceleration is calculated. Updating the position and the velocity is simpler. Again, each thread will only update the particles it's been assigned from I1 to I2. And I'll calculate the overall change in the velocity over the time of the time step, which will be the dt, or the time step size, times the acceleration. And then I'll use this time-centered form for updating the position and then update the velocity. And really, that's all there is to that. This is very simple and will run very fast. So to then run this code and submitting it as a job, here I'm going to ask for the time, the number of tasks per node, and so I can ask for I can ask for up to 128 tasks, or I'll use them as cores, and I'm going to run on one node because this is going to be a shared memory application. So we don't have the framework set up, and it would be very inefficient anyway, but we don't have the framework set up for running shared memory applications across multiple nodes. So it needs to be constrained to one node. And then I can ask memory on a per CPU basis. And there are about 4 gigabytes or 4,000 megabytes per CPU for a 512 gigabyte node with 128 cores, 4 gigs per core. And so this asks for just slightly less than that, leaving some room for the operating system and the overhead of all the processes that support the application. So I load the module that I built the application with, and then I specify the inputs in terms of the number of time steps, the chunk size, and the total number of particles, and the number of threads, and I pass those in to the program, which I just called NB for n-body. And I did some benchmarks. And basically what this is looking at is the total time it took to do a force calculation across all the particles. And what one expects as you use more cores is that the total time should decrease as you use more cores. So if you use twice as many cores, ideally, the time should go down by a factor of 2. If you completely balance the work and they're doing it with 100% efficiency. And that corresponds in this log plot to a line with a slope of -1, which actually these largest two sets of problems correspond to. So I'm doing problems in the range of from 1,000 particles up to 500,000 particles. And the two largest ones seem to be getting very good scaling, and the smaller ones are limited to how good the scaling can get. And actually, this is very illustrative of general principles in doing parallel computing, that if you don't give a thread or any process enough work to do between times in which it needs to synchronize with the rest of the system, you'll see the performance degrade. And there are very simple reasons why. For example, these high performance compute nodes have time slices that are fairly large in size. They tend to be on the order of a millisecond or 10 to the minus 3 seconds. And the reason why they use large time slices, larger, in fact, than what you typically find on like a laptop, is mainly because they want to allow for there to be large vector lengths that can be streaming through the processor to get the absolute best performance. So they'll typically be configured for very large problems rather than very, very low latency, tiny problems. But regardless, there's going to be some finite time slice when the scheduler on the processor has to dish out work and figure out which thread is doing what next in terms of advancing the giving it resources and tying it in with memory and everything else. Upshot is it's limited on just how small a time step you can take in terms of how short a time it can take. Once you hit that time slice barrier, then anything in your code that needs to synchronize on that is going to limit it. But if you give the threads enough work to do, then you can get really excellent scaling. And this is really typical of the really larger problems that would justify using this much resources. If you have a really tiny problem, then maybe you want to think about a different way of organizing things so that you can use fewer numbers of threads and maybe more tasks and break it up into more cases if you really need to scale up, for example. Here's a different way of looking at the exact same data, and it's basically more of a direct measure of what we might call strong scaling. And that's sort of a measure of the overall efficiency, and that in the sense that you would expect the total number of force calculations to increase both with time and also with the number of cores. Or another way to put it is the number of force calculations that one core does in a given amount of time should be of what other cores are doing if it's running 100% efficient. Any degradation to that due to the fact of memory bandwidth, multiple threads sharing the memory bandwidth or having to synchronize with each other would degrade the performance. And so in this space, it's perfect strong scaling if each of the threads does exactly the same number of calculations, no matter how many other threads are running. And that's emblematic of perfect strong scaling. And as you can see, the largest problems are somewhat close to that, and then the smaller ones degrade from that quite a bit. And so that's another way of looking at the same data. And then finally, in terms of tuning the performance with that chunk size that I'd mentioned, so this is to get better cache reuse. We can see how the performance will degrade if we go from the optimal value of a chunk size of around 512 particles per chunk. And that actually corresponds to a number of particles that fit into L2 cache, really local to the core. This is as complicated a curve as it is because the scheduler is trying to do the best it can. It is a very sophisticated algorithm. And so it will try to schedule in memory and threads the best way that it can to get the best performance, making all kinds of assumptions. So that's a complicated thing. But we can see that as we go to larger and larger chunk size, the performance does degrade. Now, I should point out that this is not that big a range of values between, what is this here, 3.3 or so and 3.35. So that's only a very small variation overall. You can see some variation. The variation will be much more pronounced if the problem size gets much bigger. I was doing this on only 1 million particles. But what this is emblematic of is the fact that these agate nodes are very powerful and they have a lot of cache, second level and third level cache that they can take advantage of. And so this will give even dusty deck kinds of applications, standard calculations that you're really pushing to the limits into new regimes. It will give them a chance to perform really, really well. And I think it's part of the reason why these architectures, these more recent architectures, have done so well in terms of benchmarks, because they really do support real applications in a very flexible way. And they can do so because they have so much resources that are on processor and so much bandwidth to the main memory. So it shows that it's actually quite a nice machine for doing a wide range of calculations on. So the takeaways from this is, if you really want to push performance, if you really need to do that, give each thread a lot of work to do. Make the thread the parallel regions as large as possible and minimize the times you need to do barrier syncs. And then for the really, really large problems, you'll want to you might want to look at first touch as well as, and especially cache reuse can make a big difference in performance for really, really large problems. And here is just a quick taste, really, of the kinds of steps you will go through in building and running these thread parallel codes, the tools that you have available. This is nothing more than just sort of to give you a feel or a flavor for it. You'll want to load the modules that are and we support two main categories, because these will typically be compiled codes. And the two main categories of families of software you might want to look at are Intel and the GNU compilers. So we have modules for each, and I'm only listing one, and these are probably already not the best or optimal ones to use. We have quite a few, and it will depend on the current generation. I'll point you to documentation we have for that. Then to build, you'll want to compile your code in Fortran or C. And so there's the Intel and the GNU compilers for each. And then when it comes time to run it, you may want to set up your environment not only with the module loads, but setting up these shell variables in terms of the number of threads. And then also you can control thread affinity in a variety of ways, depending on which family of compiler you're using. And then at runtime, you then finally run the application. And with the Intel compiler, you can nuance your run environment for how you assign threads to cores in a whole variety of ways, a rich variety of ways. This is no more than a taste of what you have available. And there's quite a lot of documentation that we can point you to. I just checked these this morning, and all of these sites are still live. There's a ton of tutorials you can find here and summaries. And then there are the specs for the Intel and GNU compilers, as well as all the different versions you might use. And so, again, this is a lot of information. If you delve into this and you're actually developing your own code, you can take this as deeply as you want. We're here to help if you have questions on any of this. The final example it will be using message passing or MPI, and this is for distributed memory parallel. And this is really motivated by the kinds of architectures that have really become common for the high performance computing, where you have many nodes that aren't don't directly see each other's memory, but can communicate through a very high performance, usually InfiniBand network. And so, in order to get a a program or an application to run in a tightly coupled way across a large system that's using more than one node, um, that, where the nodes can only communicate to each other through these through a network type of protocols, message passing is the way to go. So that's what actually motivated MPI in the first place. But it turned out to be a very flexible framework, and also what I found to be a very flexible framework. You can run, for example, multiple MPI ranks or on the same node. Each rank corresponds to a physical running process. And again, you have the notion of this process address space. So each rank can only see the memory that's in its own process. And it can fire off threads inside if you want. But in order for it to communicate to another rank, which is another physical process with its own separate process address space, you need to pass messages in between. And the MPI framework allows you to do that very efficiently. So I'll show you how to fire these off in the Slurm queue, as well as I'll give an example for how you can uh, use a very large amount of memory that's distributed across multiple nodes. Okay, so again, the Slurm script is going to look very similar to what we've seen before, except now we're going to be asking for more than one node. So in principle, you can run an MPI program on a single node and just have multiple ranks, and each rank might only use one core. And for some applications, that actually might be the most efficient way to do it. However, if you really want to scale up and use more cores and more memory than is available on a single node, then you certainly can do that by asking for multiple nodes. Here I'm asking for 32 nodes, which is the most you can regularly ask for. And on each one of those nodes, I'm asking for 128 tasks, which will give me 128 cores to use, which is basically all that's going to be on a standard compute node. And again, I ask for some amount of time it will run for. And I specify, and now I need to specify the queue or the partition to be MSI large. So that's the key partition you need to use in order to run on more than one node in a single, for something like MPI. Then to actually run the application, you need to have the build environment typically loaded. So that will typically be with the module load. And then you would run the task under, there's a variety of ways you can do this. And one typical way is with MPI run. What this one does is it will fire off multiple copies of your executable. That's physically what it's doing. And here I'm asking for 4,098 copies to be instantiated. And they will be evenly spread across the 32 nodes for the way this job is constructed. And it does more than just starting it. It starts up a whole bunch of a framework that will allow these separate instances of this executable, separate processes, to talk to each other via message passing. And so it not only coordinates the start of starting them up, but it will also coordinate how they can communicate with each other and do barrier syncs and share information. The example that I have is was motivated by, in fact, some of the peculiarities of our Slurm queue. A lot of users are running into issues where they would start off um, many ranks and that would go across many MPI ranks that would go across multiple nodes, and the job would hang. And what it turned out was is that all the ranks are asking for memory, and if you don't allocate memory correctly or request memory correctly, um, the all the memory you request will go onto just one of the nodes, the first node, and the other nodes won't know anything about the memory request. Slurm has that flexibility. And I should return here to say that when you submit the job, it's a really good idea to ask for memory on a per CPU basis. So again, I'm asking for this is memory per CPU, and the default is in megabytes. So this is asking for 3.9 gigabytes or 3,900 megabytes. And that's a good for the agate cluster, that's a reasonable amount of memory to request on a per CPU basis, because you won't, even if you ask for all 128 cores, this will ask for just under the total memory of the machine, basically. And so it's a fair amount of memory per CPU, and I like to do that so that it's evenly divided across CPUs. And this will guarantee that the ranks on even the second and third and fourth node will be getting the memory that they need in the same way that all the other ones are. So this is a good thing to do, but I wanted to come up with an application that would actually demonstrate that and prove that it was working so that I could use this to diagnose in case, for example, a user came to me and had a problem with memory on some of the ranks. This would be a good test case to see, okay, has the system gotten broken with some software patch? If so, I can then use this code to help operations diagnose it. But more typically, there'll be something in the user's environment or the way they're setting up the job, and then we can use this code to help diagnose their environment and help them get up and running. So it's proven to be effective that way. And it's a nice way to illustrate how you can really ask for a very large amount of memory and really, really get it and demonstrate that you did. It also illustrates some of the basics of how an MPI code runs, though it doesn't go into full detail. That again is a very rich subject. But the basics then is that after you've run MPI run, you will have some number of instances of this program running. So there will be separate running tasks or processes, I should say. And each one of those processes are running independently, and they will pretty much do the same thing until you start coordinating them through the MPI framework. And the way you do that is with this MPI init. So that will initialize the environment for this process to tie it in with the overall set of MPI ranks so that it will then have the ability to talk and send messages back and forth in a variety of ways. So one of the most basic things you can do then is once you've done this MPI init, is you can do these calls like MPI com size to get the number of ranks that you started up. Similarly, you can do this MPI com rank that will return the rank that this particular process is running under. And again, just like the thread number and like the Slurm task ID, this is the most basic way that you have of dividing up the work to tell this process which piece of the work it will do out of all of the work to be done across all the different ranks. And then here, I'm just going to do a simple calculation that will guarantee that I've allocated all the memory that I've requested, and it will be simultaneously allocated on all ranks at once. and only return an answer total, which is a kind of a very cheap checksum that can only be the right value if they all got the right data and um, and summed it up correctly. So it's a sort of a really hard, a simple test to ensure that all the memory really did get allocated, and then I report the results in terms of the number of nodes that ran, the number of ranks, and the this total checksum, as well as the expected value, which I calculate analytically here, and only report on rank 0. Um, so only one of the ranks will report it. But as long as the total that I get back matches the expected value, then I know that the program as a whole worked. And then finally, you can bring down the MPI framework or the environment by doing this MPI finalize, which is a nice thing to do to ensure that it cleanly terminates the program before you exit it. So this calculation routine, basically all it's going to do is it's going to allocate memory, and I'm going to use these allocatable arrays so that I can specify the number of megabytes. And I do that by having it be a real star 8 or double precision floating point. So I have 8 bytes per number. And by using 1/8 of a million elements, I can then ensure that each one of these 1/8 of a million elements per row, I guarantee that each row has 1 megabytes worth of data, and then the number of rows gives me the number of megabytes that in total that are in this array, and that's how I guarantee that I allocated that much space. And then I use this construct here to actually assign the array the value, which is just the thread number, and then I do an MPI barrier here. And at this point, the memory has been allocated and committed because it's actually been assigned a value. And so once all of the MPI ranks reach here, they've all allocated the memory that I've expected, and that guarantees that I've really exercised the machine and used that much memory. Then to do the check, I just simply sum up all the elements in the array. And this gives me my checksum that needs to match that analytic form for it. And then I use a MPI construct, this reduce, which will combine all of these results into one by summing them together, this MPI sum. And then I can deallocate the array and return, and it will return this value in the total. And then just for fun, to calculate the number of nodes, I actually use a bit of an arcane construct to get the process name. This is a way you can get the actual, within the code, get the host name that you're running on. And then I'm using a different MPI construct, an MPI gather, to collect all of these host names from all the different ranks onto rank 0. And then I go through this and count the number of independent names I got back to get the number of nodes I was running on. Then finally, to run this, here I'm going to run on 8 nodes with 128 cores each. So I'm asking for the entire node. For each of these nodes, I'm asking for all of the cores and almost all of the memory, 3,900 megabytes per core. And then I can then basically run this code. Here it's, because I'm running on 8 nodes, 128 cores each, it'll be 1,024 ranks. And I'm asking for almost all the memory I'm asking for, that I have available in my job, so 3,800 megabytes. And then I report the results in terms of ranks, hosts, and the totals, and sure enough, the checksums match out. So I know that the code worked correctly. And so this is a relatively simple example. I haven't only touched on the message passing that's possible just in terms of the gather and the reduction. There's a much, very rich set of things you can do with this, of course. But this is a nice test code for really demonstrating that your environment can really allocate the memory that you're expecting for your application to run. And there's, again, a ton of documentation that's available on this in terms of tutorials, specifications, and examples. And then we have our working examples posted here. If you try these, some of the compiler versions may have changed since, but we can work with you to help you get those running if you have any questions on that for sure. And then finally, an overview. Well, we've talked about a variety of different ways you can do parallel computing that are available here at MSI and on the Agate cluster. And it's really motivated by the rapidly changing hardware and the nature in which it's changing, in which the core counts are going way up and the bandwidth is per core is going down because we're getting such large high core count nodes. This can motivate and support, but also support a variety of different ways you can do your calculation. And the nice thing is you can use them in any combination or all together. And they form a kind of a natural hierarchy, where the top of the hierarchy is the overall workflow itself. And so this might correspond to multiple independent cases that you would run that you would process, and they would be naturally supported by a task array. Then for each one of the task arrays, each one of these tasks could run any of these parallel constructs, starting maybe with MPI, so that each task in turn could actually fire off processes on one node or on several nodes, and which would be connected through the message passing interface that MPI gives you. And then each one of those processes in turn, each MPI rank, could fire off an OpenMP parallel region or do its own threading model, however you want to do that. So you could have multiple threads within each MPI application, within each MPI rank. And then finally, those threads can in turn drive GPUs or SIMD type constructs for kind of a vectorization level, where the GPUs you'd have grids like Angela was describing with the CUDA code, or SIMD for more general CPU type constructs. So this gives you a lot of flexibility and a lot of compute power for your applications. Which ones you wish to use will depend on the nature of your application. And if you don't already have an implementation that you want to just port and use, you need some help, we are certainly here to help you discuss what the options are and find a good solution for what you're trying to do. And with that, I'll open it up to questions, and thank you very much.